All right, if the domain of a function is all real numbers, any number can be used as an input value. Remember when they use that word input value, they're talking about an x value. This process will produce an infinite number of ordered pairs that satisfy the function. Therefore, arrowheads are drawn at both ends of a smooth line or curve to represent the infinite number of ordered pairs. If a domain is not given, assume that the domain is all real numbers. So this is really, really important because how do you know when you're dealing with the first example that we did when there was a limited domain versus a domain that has of the function that is all real numbers? And so this is the key. If a domain is not given, assume that the domain is all real numbers. Okay, so let's look at one of our previous examples briefly here. So we have this function, right? And you can have a function or an equation, right? This is function notation, it's f of x. It could easily be written as y equals x squared plus 2. All right. So we have this function, but it is giving us a domain. That means it's limited. That means we're going to only be graphing particular points. In comparison, here is an equation. This is going to be the first one we're going to look at today. And it just says graph the function. There is no domain listed. So since there is no domain listed here, so if a domain is not given, assume that the domain is all real numbers. And what it means is if, we're going to go back here to the beginning, if a domain of a function is all real numbers, any number can be used as the input value, which is the x value. So when we're trying to graph this, okay, so we look at this, we see there is no given domain. That means it's going to be all real numbers, which also tells us we are actually going to be graphing a line and connecting the points. But when we go to graph it, we can really pick any input values, all right? It doesn't matter. Now, I'm going to tell you some input values that I like to pick, which is just kind of standard, but know that you can pick any number can be used as an input value if the domain of a function is all real numbers. Okay, so here's a little table here, graphing functions using a domain of all real numbers. So step 1, use the function to generate ordered pairs by choosing several values for x. Step 2, plot enough points to see a pattern for the graph. And then finally, step 3, connect the points with a line or smooth curve. All right, so let's go ahead and get started with our first example. So here we have example 2a, and we just need to graph this function. So it's nice this function is already equal to y, right? Negative 3x plus 2 equals y, so y is already by itself. And so the values that I like to pick are usually around 0. So I like to choose 0 and then 2 values on the negative side of 0 and then 2 values on the positive side of 0. So the input values that I like to pick are just negative 2, negative 1, 0, 1, 2, and 3. And I would suggest you picking these same values when you graph your functions as well. All right, and now we're just going to go through the process. So we're going to stick all these input values in. We know that we are going to get these ordered pairs, and we're going to graph those ordered pairs. But because the domain is not limited, we're going to connect those dots, and so we're going to end up with some type of line. So let's go ahead and figure out what those ordered pairs are. So first I'm going to stick these input values into this function so we can figure out what y is. So negative 3, I'm substituting negative 2 in there. Negative 3 times negative 2 is positive 6. Plus 2 is equal to 8. So we end up with this point, negative 2, 8. I'm going to go ahead and do the next point 1. So negative times a negative is a positive. 3 times 1 is 3. And then we have the next one here. Negative 3 times 0 is 0. Plus 2 is just 2. Then we have, we're going to stick in 1. Negative 3 times 1 plus 2. Negative 3 times 1 is negative 3 plus 2. Negative 3 plus 2 is negative 1. Oh, did I forget to write these ordered pairs? You're like, what are you doing? Okay, so this one is negative 1. I think I just kind of got in a groove and then kept going with it. 0, 2, and then 1, negative 1. All right, let's keep going. Negative 3 times 2 plus 2 equals, negative 3 times 2 is negative 6 plus 2. Negative 6 plus 2 is negative 4. That leaves us with the ordered pair 2, negative 4. This is my x value, this is my y, right? Ordered pairs are made up of x and y. And then we have negative 3 times 3 plus 2 equals, negative 3 times 3 would be negative 9, plus 2 would give us negative 7. So the ordered pair is 3, negative 7. Perfect. Now we're just going to go ahead and plot all of these ordered pairs. So negative 2, 8 is right here. Negative 1, 5 is here. 0, 2, 1, negative 1, 2, negative 4, 3, negative 7, right there. And that's it. So we've created our table. We're going to go ahead and graph this function and see what it looks like by connecting these dots. And get my straight edge. I always like using a straight edge so the lines are really straight. Okay, and there is our function, but the domain is all real numbers, so because the domain isn't listed, so we need to make sure that we put arrows on the end of the line, which tells us that this line goes forever this way and forever this way in both directions. All right, that is it for that first example. Let's go ahead and look at our next example here. Okay, trying to get it all in there. Okay, so we have to graph the function, and if you notice, graph the function g of x equals, this is the absolute value plus 2, all right? There's x values here, so we're going to kind of use those same ones that we used last time. Negative 2, negative 1, 0, 1, 2, 3. Excuse me. Okay. All right. Yes. So we're going to stick in these domain values into this function, get ordered pairs. Oh, look at this. This is fun. Let's go ahead and break this down. Okay. So right here, we have this. We know that the ordered pair, usually for all of our tables, over here, it's been x, y, right? So we're used to seeing this. But now we have this x g of x, which is a little different. But that's still a point, right? Because our x is still x, and g of x is actually the same thing as y. So whether you write y or you write g of x here, it means the same thing as an ordered pair. So I just wanted to talk about that because that's just a different way. Usually we're used to seeing ordered pairs expressed like this, but you can see this as you get up into higher mathematics. And when you see something that looks like this, you know this is x, you know this is y, you know that whatever the information is just an ordered pair, and everything you know about ordered pairs is going to apply to the same information here, because all of this is just an ordered pair. It's just a more complicated way to write it, which when I used to see this before I kind of made that connection, I was just really intimidated by the way that this looked. But once I realized, hey, g of x is actually the same thing as f of x, which is the same thing as y, oh my gosh, this is just a point. I know how to plot points. I know how to figure them out. So I think it's just really, really important to make that connection. Okay. So let's go ahead and figure out what these values are. I'm not going to write g of x in here because I only have a limited amount of space. So I'm just going to stick this x value into the absolute value here. Okay, the absolute value of -2 is 2. So we end up with 2 plus 2, which is 4. So our first point, -2, 4. And then we're just going to figure out the next one. Absolute value -1 plus 2. Absolute value -1 is 1, which is 3. And then we have the absolute value of 0 plus 2, which is just 0 plus 2, which is 2. And then we have the absolute value of 1 plus 2. The absolute value of 1 is 1 plus 2, which is 3. And then we have the absolute value of 2 plus 2. Absolute value of 2 is 2, because the absolute value of any number is the number just positive, same number positive. 2 plus 2 is 4. We have 2, 4. And then the absolute value of 3 is 3, which is 5. All right, and then we just go ahead and plot these points. So -2, 4 is right here. -1, 3 is here. 0, 2 is here. 1, 3 is here. 2, 4 is here. And 3, 5 is right here. So we have enough points to graph this function. So I'm just going to go ahead and try to graph it now. I got to find my little straight edge. It fell on the ground. Okay, so if you look, I really love absolute value functions because they're just a fun shape. So it goes here, and we're going to put an arrow because it goes forever and ever that way. And then it goes this way. Like this. And the cool thing about absolute value functions, anytime you see an absolute value function or absolute value expression in a function, the shape of it is always going to be a V. Now this V might be pointing up or it might be pointing down, but it is always a V. So I really like just being able to sometimes look at the functions and then have an idea what that picture is going to look like before I actually graph it. So yeah, absolute value functions are always going to be a V. Whenever you have something where there's a regular y and a regular x, it is always going to be a line. So yeah, if you are graphing something and you know just by looking at it, it's supposed to look like a line, and then when you start graphing these points, it isn't in a line, that means that you probably messed up on one of these as you were solving one of the points. And so you need to go back and look at your work because all the points should line up as a straight line. And when you're dealing with an absolute value, if you don't have something that looks like a V, then you need to go back and look at your work again because you probably, it's just a nice way to check yourself. So if you understand what's going on, you can kind of check your work visually because this should be a V, the other one should be a line. All right, now it is your turn, ladies and gentlemen, to check it out. I want you to go ahead and graph the function here for all, right? The domain isn't listed. That means you know that you're graphing it for all real numbers. You're going to pick your numbers. Go ahead and pick the same ones that I picked. You can pick any ones, but we want to kind of just stick with these for this lesson. Fill in your table, graph it, and then just make sure you connect that line because the domain is all real numbers. So here's my friend the pause dragon. Remind you to pause your device, work out this problem. When you get done, press play and we'll go over it together. All right, let's see how you did. We're going to go ahead and graph this function. This is, right, f of x is equal to y. So this is a regular y, regular x. I know this is going to be a straight line. I'm going to go ahead and pick some domain values, -1, -2, 0, 1, 2, 3. And then we're just going to substitute those into this function here. I'm not going to write the f of x. I'm just going to write 3 times a -2 minus 2. 3 times a -2 is -6, minus 2 equals -8, which leaves me with the ordered pair, -2, -8. And we have this, right? This is the same thing as x, y, but instead of writing y, we're using f of x. Okay, so let's go on to the next one. We have 3 times negative 1 minus 2. 3 times negative 1 is negative 3 minus 2 is equal to negative 5. And then, oh, ordered pair. I get kind of like want to just get going with this, and then I forget to write the ordered pair. All right, so let's do the next one when x is 0. So 3 times 0 minus 2. 3 times 0, 0 minus 2 equals negative 2. We end up with the ordered pair 0, negative 2. And then let's figure it out when x is 1. 3 times 1 is 3. 3 minus 2 is 1. So nice. And then let's figure out when x is 2. 3 times 2 is 6. That's 4. 2, 4 is the ordered pair. And then lastly, when x is 3, we're just sticking it into the same thing. 3 times 3 is 9 minus 2, which is 7. So our ordered pair is 3, 7. Now it's just time to graph these ordered pairs. So negative 2, negative 8 is right here. Negative 1, negative 5 is here. 0, negative 2 is here. 1, 1 is here. 2, 4 is here. And 3, 7 is right there. And now we can just go ahead and connect those dots. Whoops, kind of messed up on my line there. There we go. That's better. And you got to put arrows because it goes off in both directions forever and ever. So if you have this, awesome job, great work. If you don't, go ahead and fix your work, fix your graph so it looks exactly like mine. All right, let's go ahead and work on this next one. Check it out, example 2b, all right? So you're gonna graph this particular function. So go ahead and pause your device. When you get done, press play and we'll talk about it together. All right, see you in a bit. All right, let's see how you did. So we have this lovely absolute value function. So you should have something. Remember, whenever you have an absolute value, it should look like a V. So you should have some type of V figure. So let's go ahead and pick our normal values, negative 2, negative 1, 0, 1, 2, 3. And then we're just going to substitute those into this equation. So we have, you know, I'll just do the absolute value. Sticking negative 2 minus 1. Negative, you have to do this inside of the absolute values first. You got to combine that. Negative 2 minus 1 will be the absolute value of negative 3, which is a positive 3. And so our point is negative 2, 3. Let's go ahead and do the next one. So we're going to substitute x in, negative 1 in for x. So we have negative 1 minus 1. Negative 1 minus 1 would be a negative 2. Absolute value of negative 2 is 2. All right, and then the next one is 0 minus 1. 0 minus 1 is just negative 1. The absolute value of negative 1 is 1. And then we have when x is 1, so 1 minus 1 is 0. And then we have when x is 2. 2 minus 1 is 1, absolute value of 1, which is, oh, I should have done this. We have to simplify this. 1 minus 1 is 0, and then the absolute value of 0 is 0. Okay, that's how you'd write that. And then 2 minus 1 is 1, and then the absolute value of 1 is 1. So that ends up with the point 2, 1. And then finally, when x is 3, we have 3 minus 1. We simplify that. 3 minus 1 is 2. The absolute value of 2 is 2. So we end up with this point here. And now we just need to go ahead and graph those points. So negative 2, 3 is here. Negative 1, 2 is here. 0, 1 is here. 1, 0 is here. 2, 1 is here. 3, 2 is here. And you can kind of start to see that V shape again, right? And then we just connect the dots. And then over here as well. And then there we have it. We have our lovely absolute value graph. So if you got that, yo, good, you did a wonderful job, and we'll see you in a little bit for example 3.